Now, which part of the brain have we described? We described the cerebrum, we described the diencephalon. Now let's describe our little brain, which is the cerebellum. And the cerebellum, let me show you in here in my in this app, the location of the cerebellum. So it's located, is the organ in purple. So can you see that it's located right inferior to the occipital lobes, right? Here posteriorly, right inferior to the cerebrum and posterior to the brainstem, okay? So that's the cerebellum. And as you can see, it consists of two lobes or two cerebellar hemispheres, just like the cerebrum. But instead of being divided by a fissure, like in the cerebrum, this is divided by a piece of gray matter that is called the vermis. Okay, so that's the location and the gross anatomy of how the cerebellum looks like. So this is a sagittal section through the cerebellum. So we can see, and we'll describe, I'm going to put several things together later on. So I want you to keep everything here. This is one cerebellar hemisphere. So that might be the right one. So you can see that in the surface we have gray matter, and all of these that looks like the branches of the tree, that is called arbor or arbora vitae, and is the white matter of the cerebellum. And deep to that white matter is not seen in here, but we have areas of gray matter. So the organization of the gray and white matter, it resembles the one of the cerebrum. Now, this white matter is actually these white axons or myelinated axons are communicating the cerebellum with other parts of the brain, with the pons, with the medulla oblongata, actually also with the spinal cord, and up with the cerebrum. Okay, so let's see what it does. What the cerebellum, well, I don't know what is that. Okay, so what the cerebellum does is that it coordinates our skeletal movements. So it creates the pattern so our movements look smooth and not jerky. Okay, so to do that, the cerebellum receives information, sensory information, right? That's what how we receive information. So from where? From, my God, I have to learn how to draw an ear, but that's looks like a fetus, but that's an ear. And right here in the inner ear, remember that we have the organs that keep our balance and equilibrium. Those organs, the receptors in there, send sensory information about every millisecond. It sends sensory information about the rotational movements or balance of our head, okay, or position of our head. Also, it receives information from the muscles and tendons and joint capsules. So remember, in there we have proprioceptors, and that information again is by the second, or every millisecond is being sent to the cerebellum. So the cerebellum knows at every millisecond the position of your head and of your muscles and of your joints, the degree, the angle, the degree of angle of every joint. But also receives information about the motor cortex, which is about there, right? Remember, in the precentral gyrus. So what happens is that the cerebrum says, let's go back to our example with the fly. the cerebrum says, I want to fly, to whack that fly. And in order to do that, you need to contract the muscles of your arm and forearm to contract, to whack the fly out of place, right, out of your sight. Now, the cerebrum, before doing that, it sends the command. Before reaching the spinal cord, it sends the command to the cerebellum. And the cerebellum right here assesses that information and compares that information with the one being received by the inner ear and by the muscles, and says, he wants to, let's say the cerebrum wants to contract the abductor muscles and flexors of the arm. But if he does that, well, let's see, the head is at this moment is turning to the right. He's actually moving his head, and the position of the body, and maybe he's sitting down and he has a wall behind it. So all of that information is analyzed and assessed in the cerebellum, and then adjust all of the movements. And it says, instead of contracting the abductor, because you're gonna bump the chair like I did, so instead of contracting that, let's relax let's say the extensors and contract the flexors a little bit more, and to this angle, so we can avoid falling. That's the main function of the cerebellum, to keep us from falling, and to coordinate the logistics of all of these patterns of muscle contraction of the extensors and the flexors, the adductor and the abductor. All of that logistics, all of the planification occurs right here in the cerebellum. So the cerebellum receives the information, we are here, receives the information from the cerebrum, from the motor cortex of the cerebrum in here, okay, sends it to the cerebellum. The cerebellum compares what the cerebrum wants to do with the body position, the head position and the body position, and then is going to send back the instructions to the cerebrum again, to the motor cortex, and say, let's do that instead. So it refines the movement. So from there, from the motor cortex, that information gets down to, well, I don't have there, but to the spinal cord. From the spinal cord, this motor neuron sends the command to the skeletal muscle fibers involved in the movement, and we have these beautiful, smooth, non-jerky movements that we do every day and for every task. Now, look at everything that happens just in the matters of nanoseconds. So the information goes from the cerebrum to the cerebellum. The cerebellum compares with the inner ear, with the skeletal muscles, joints, and tendons, and then goes back to the cerebrum, and the cerebrum sends it to the spinal cord, and the spinal cord sends it to the skeletal muscle, all in nanoseconds. For every, look all the movements that we're doing at this time, and for every movement, the cerebellum and the cerebellum does that. That's what I call teamwork. Now, this applies to every skeletal muscle, including the ones that we use to vocalize. Talking is not easy. It's a pattern. The cerebellum has to control the pattern between our breathing movements, our digestive, the swallowing the saliva, although otherwise it will look ugly, we will look purple if we stop breathing and we stop swallowing the saliva. We will be drooling at the same time we'll talk. So the coordination of all of those movements and the coordination of the contraction of the muscles in the larynx that control the vocal cords, with the muscle of the facial expression to move our lips, and the the movements of the tongue, all of that happens in the cerebellum to create, so we can uh, talk and create speech. Not functioning right now. What else is also a side of higher functions, cognitive functions, just like the cerebrum. Um, so in here, whenever we, well, as I told you, is involved in language, learning also a new language, learning a new motor skill, learning to drive your bike, the coordination that it takes to ride your bike or ride your car. Do you remember the first time you were riding your car, and you know that the coordination between your foot, put it in the brake, put it in the gas pedal, plus the uh, uh, your hands on the steering wheel, the how to put your signal light, all of those coordinating movements are, the logistic happens here in the cerebellum to a point that at the beginning, while we're learning these movements, it might look jerky and uncoordinated until we learn the routine. And learning that routine, that pattern of movement happens in the cerebellum. To ride the bike, to ride a car, to write in or learn any new skill. I put here tennis because not so long I decided I want to learn how to play tennis. Those movements at the beginning, just putting the ball in the air and at the same time putting your racket back so you can hit, hopefully, the ball with the racket, all of the coordination of movements at the beginning jerky, but then they happen without your automatically. You don't even think about it. All of that happens on the cerebellum. Learning how to ski happens. All of those new skills happens on the cerebellum. So what happens if, I know the picture is blurry, but I didn't find a better one. But what happens if the cerebellum gets damaged, gets injured? Parenthesis, we don't need a damage, an organic injury of the cerebellum to have these symptoms. Alcohol in less than 10 minutes can do that. Okay? It's like about the second and the third structure in the brain that is reached by the cerebellum, by the alcohol. So what it's going to do is block everything I have told you before. So we are not going to be able to keep our balance or equilibrium. So just imagine a drunk person. How do they look like? They're walking like that, right? Like they cannot walk a straight line. So actually, people or individuals with cerebellar injuries, what they do, and this is automatic, they walk with the legs open. These are the legs, trying to increase the base, the stance of in the center of gravity of for them, so to avoid fall. So they walk like a penguin, kind of, but with the legs opened. What else? They cannot coordinate movements. For one of the ways we evaluate that is just doing alternating movements, like turning your hands up and down, the palm of your hands, or touching your nose and then something that is moving in front of you like a pen. So if your cerebellum is working properly, you will do, even with my eyes closed, I can do this because I'm the one holding the pen. Persons with impairment, the cerebellar functions cannot perform those movements, or if they do it, the movements are going to be all jerky and unsteady before reaching the target. In general, they're going to have jerky, overreaching movements, prone to a lot of accidents um, because the cerebellum is affected. Okay, so this is a little bit of what the cerebellum does. Next video, we are going to talk about the last part of the brain structure, which is the brainstem. See you.